Welcome. Today we're going to talk about mcpGraph, which is our no-code code mode solution. Hopefully that'll make more sense if it doesn't already. It's a fast, secure, reliable, observable MCP tool aggregation and orchestration solution, which is a mouthful, but let's just dive in. So what is code mode? There were 3 papers or blog entries all around the same time in late September, early November of this year by Cloudflare, Anthropic, and Docker that all introduced the same concept and they all used the same name for it, which was code mode. And I'll talk a little bit about what that is. These papers are all pretty short. They're definitely worth looking at. I don't disagree with any of the reasons for this, and I think the way they did it makes sense. I just have a little bit of different idea of how I think it should work. So we'll explore that. So the basic concept is the traditional tool calling is problematic in a couple of ways specifically. First of all, the notion that tool definitions overload the context window. We've seen a lot of solutions around this, around sort of MCP tool optimization and tool searching and different ways to kind of abstract from that. But the general idea is if you have even a few MCP servers installed, you can easily generate hundreds of K of tool descriptions for all the dozens of tools that those MCP servers provide, even when they're rarely relevant to the task that the agent's trying to accomplish. So that costs tokens. And then the second thing, which maybe is not quite as obvious, is that when you're doing sequences of tool calls, the intermediate tool results consume additional tokens. So the example that they give in the Anthropic paper, they give a few, but the first one is this notion that they want to read a transcript from a Google Doc and they want to add that to a Salesforce prospect. So they're going to call a single MCP function tool in Google Docs to get the transcript, and then they're going to take that transcript and stick it onto the Salesforce prospect by calling a Salesforce tool. So what does that mean? That means, first of all, that you're going to have a Google and a Salesforce MCP server installed in your agent, which means you're probably going to have dozens of tools that do all kinds of things you don't care about. And all those tool descriptions are going to be in every single request you send to the model. So that's a ton of context, easily hundreds of K. But secondly, when you call Google Docs and it gets that transcript document back, and who knows how big that's going to be, that transcript document also goes onto the context stack. It also chews up tokens, not just once, but every transaction for which it's still in the stack. And it does so because all of the tool calls that you make and all of the responses and all the data in those responses are just all sort of part of your conversation history and your context. So you're accumulating all of this context that is not meaningful at all to the process that the agent's trying to accomplish, just to be able to hand it from one tool to another tool. So a lot of the sort of, tooling around giving you the appropriate tools for the given context that you're in, that sort of tool optimization, they sort of handle the first part, but they don't really handle the second part, which is you're still going to call those tools and have all that intermediate data. And the problem with that is you're using a bunch of context, which means that costs you time and money, but it also makes the models much less accurate. And this is a little bit of a two-edged sword, because if you use an expensive model, it's not going to suffer as much from the accuracy problem by having competing goals and lots of context. It doesn't have to do with what it's doing because it's smarter, but it costs more. But if you move to a model to try to minimize that cost, if you move to a local model or a model that's maybe not quite as cutting edge, you're not going to pay as much for the context, but you're going to have significantly worse reasoning results and accuracy because of all that confusion, right? Now the model has to, not only solve the problem you wanted to solve, but it has to figure out which tool to call and what order to call them and what to do with the tool input and output and all that sort of part of its goal orientation. So it's a problem. And what all 3 of those papers suggest that we do about that problem is this thing called code mode, where essentially you take the agents and you have agents write code. In all 3 cases, they chose JavaScript or TypeScript. So you essentially have the agent create an MCP server in that language that calls the other MCP servers and sort of routes the data between them and returns a simple response. And agents are pretty good at this. So you can tell an agent, hey, go make me an MCP server, have it call these other MCP servers, have it, do this. And they can go write you some TypeScript or JavaScript code to do that. And so with code mode, in that same example, they just have the agent build it a new tool called move transcript to prospect, and that tool does exactly what the agent would have done before. It calls the Google Docs MCP server, gets the output, calls the Salesforce MCP server, tacks it on there, and it returns a nice, concise result. So now none of that stuff's happening in the agent or the LLM anymore. It's all happening in this external tool that's been written by the agent. And again, from the Anthropic paper, their quote was, code execution with MCP improves context efficiency. And in their example, they reduced the amount of context token usage by 98.7%, almost all of it. So it not only made it faster and cheaper, but it also made it significantly more accurate. So generally, there's a real problem. This solution is a real solution that definitely works, which is why people are excited about it. But the problem with code mode, the problem I have, and my joke is it's right in the name, It's the fact that it's code. That even with sandboxing and hardened tools, there's still security concerns surrounding any code. So even in those examples, you have access to a bunch of tools that talk to Google Docs and a bunch of tools that talk to Salesforce, and you might have tools that talk to GitHub and who knows what else. And all those tools are capable of providing data that you wouldn't want to have exfiltrated, and they're all capable of exfiltrating data, publishing data to public repos, publishing data to public Google Docs, triggering email sends with content in Salesforce. I mean, there are holes all over the place. Even if the tools are hardened, and even if you try to scope access rights as much as you can, it's still just a huge attack surface that you have to worry about. And maybe I'm overly pessimistic because I've spent decades in information security, but I worry about code. And I especially worry about code generated by LLMs. Because the other thing that we know is that it's currently very easy, and there are many, many attack vectors where we can use malicious intent, prompt injections, all kinds of techniques to get agents and models to do things, to do emergent behaviors, or use tools that we give it to do whatever the attacker wants. And that would include writing this code, writing the code that's going to run these tools. So I think it's even more of a problem than it would be if it was just calling regular code that was just sort of out in the wild, because this is code generated by the LLM. And as with any code, it can have bugs, it can be unreliable, inefficient, not scale, has all the problems the code can have, all things that you have to manage. And it's also difficult to observe and detect through casual inspection, meaning there's not just one place I can say like, okay, what is this tool that the model made? Where is it? How is it using it? They're all done a little bit differently. In many of the cases of the examples, they're directories full of many files that are, including wrapper files that are used to implement these things. So it's sort of hard to just say, can I just go look at this code and know exactly what's happening? And code is still code, right? So when we have all these prompts and artifacts and sort of little pieces of data sitting around in our AI applications, it's sort of easy to just say, well, these are just part of this solution that's just big magic black box that we don't really know how it works anyway, so it's all fine. But as soon as we make part of this code, I mean, code is code. we have ways of handling code in organizations. We have compliance requirements. Like once something becomes code, we have a bunch of questions. Like, and this is just a short sample, but who's going to maintain it and how? Is it a language that your team already knows well and is going to be an expert in to be able to interpret that the code is doing what it's supposed to do? Are you going to make it comply with coding standards? Is it going to be in version control? Are you going to require human review and approval? Are you going to look at it for bugs, performance, scale? Are you going to do static dynamic security analysis and other things you might do in CI/CD? Security reviews, there's 100 things more than this. Once something becomes code, we have ways of handling and managing code, and those ways have to apply to this code also if you're going to use this mechanism, which I think is a problem. So what about a no-code code mode? That's the premise of this whole presentation. So if we had something that could orchestrate MCP tool calls with data transformations and conditional logic, that's the baseline of what we're talking about. Something that solves all the code mode examples, all those, several examples in each of those papers and more, but like that's the gist of the kind of problem we're trying to solve. We need something that's simple and easily authored by humans or LLM. So we can't just create some bespoke, crazy format that then we have to teach the models how to make. It's got to be something they can build as easily as they can build code. It needs to be something that's 100% predictable and reliable and fast. And it needs to be something we can observe and inspect, either as humans or with large language models or in code. And by inspect, I mean we can look at it in one place and understand exactly what it does, and it does what we want. And by observed, I mean we can watch it when it runs and make sure it's doing exactly what we expect and not anything we don't expect. And what might be some prerequisites for this? So first of all, I'm looking for something that's open source. So N8N might have been an option, but the license precludes that. Also something with no embedded programming language, and that would include things like N8N, but also Zapier and Workato and a bunch of other things, where if you can sort of jailbreak out of a framework to get into running code, then you're right back to the code problem again. You're right back to malicious injection of code. So it has to be a system that doesn't have a programming language that you can jailbreak into. And it needs to be something, as I said before, that's composable by agents out of the box. So that's something with a simple and familiar syntax and encoding, so we don't need to train or fine-tune any models to understand how to build these things. And something that uses building blocks that models have already been trained on. And I'll give an example of, there's a lot of stuff from the MCP spec, but also one of the things that we're going to talk about is this thing called JSON-Ada, which is a data transformation language that does filtering, formatting, extraction, a bunch of other stuff. It's been around for a long time. There's lots of examples, lots of training data on the public internet. And JSON Logic, which is sort of a similar toolkit for doing conditional logic, also been around for a long time, lots of training data. And all the models that I've tested with know how to do both of these things out of the box without any special prompting. So let's get to mcpGraph, which is the solution that I'm proposing here. So mcpGraph is a domain-specific language for MCP tool aggregation and orchestration. It includes declarative configuration, so we define our tools and their execution graphs in a YAML file. It includes data transformation, so we use JSON data, which is an expression language that transforms data between nodes. It's super powerful, but all it does is transform data. For conditional routing, we use JSON logic. Again, super powerful, but all it does is conditional branching. It's observable. Every tool call, transformation, and decision is traceable, auditable. You can watch it in real time. And there's no embedding coding language. So there's all the logic expressed is using the standard expression languages, JSON data and JSON logic. No JavaScript anywhere in here. So mcpGraph is available now via NPM. You can install it. You can go look at the GitHub repos. It's open source under the MIT license. So let's talk a little bit about how one of these graphs works. So an mcpGraph is a definition of an MCP server and the tools it exports, where each of those tools runs a graph to orchestrate other MCP tool calls. So hopefully that'll make a little more sense when I sort of show you an example. Basically, we have a YAML file that contains a server definition, which uses the standard MCP server metadata. So it says, hey, here's an MCP server. It has tools that it exports. So it's, again, same standard MCP tool definition. So it tells you what tools it's going to export. It has a set of MCP servers that it uses itself within the nodes of its graph. And then it has a graph. It has a set of nodes that are the individual graphs that actually run through the orchestration. The graphs can have different node types. So there's an entry node, which basically takes the MCP tool call and it maps the input parameters to this entry node. And then you can have MCP nodes that call an MCP tool. You can pass arguments and process the response. You have transformation nodes, transform nodes, which transform data. You have switch nodes for conditional routing, and you have an exit node, which returns data from the exported MCP tool as its output parameters. So what do these files look like? So it's a YAML file. It's going to have a version. It's going to have this MCP server metadata, which again is exactly the same metadata structure as is in the MCP spec for server metadata. It's going to have an MCP servers config, which is the exact configuration you would have in any kind of agent that had MCP servers configured in it. So these are the MCP servers that the nodes can use to do their work. It's going to have tools that it exports. So in this case, we have a simple, so our server is called file utils. It's file utilities, and it has one tool that it exports. It's called count files. So again, this tool description is exactly the schema of a tool description in MCP, which means agents know what it is and how to build it. So we have a tool called count files. It counts the number of files in a directory. Its input basically takes an object with a directory property that's a string that tells us what path we want to look in, and it returns an output that has an object with a count that tells us the number of files in that directory. So we're basically making a new MCP server that's called file utils, and it has a tool called count files. And then what that tool does is it runs this graph. And so this graph basically has an entry node that takes the parameters from calling the exported tool count files. It calls lister. And its next node is list directory node. So it calls this list directory node, which is an MCP node. It calls the file system MCP server, the list directory tool, with an argument, which is the entry count files node directory parameter. So this is the directory parameter passed into the function. When that's done, it transforms and counts the files, goes to this count files node, which has a transform. So this is a JSON data transform. So it essentially makes a new output node. There's an object that has a count attribute, and that is taking the list directory node, the output from this previous command. It's splitting it on new lines because they come out one per line, and it's counting those. So it's just basically counting the number of lines that were in this output, and we happen to know that correlates to the number of files. And then we have a return node that just returns this object from the MCP tool call. So pretty straightforward, and you can kind of visualize it like this, and I'll show you a visualizer that does this for you, but it's an entry list directory, count files, exit. Pretty simple graph. And when you look at this, this is inspectable. We know exactly what it's going to do. There's no code, no opportunity to inject any malicious behavior here. So the way that we run this, if you wanted to run this exact file that we just showed you to have that tool available in your coding agent or any MCP tool client, this is just an MCP server. So you can npm install mcpGraph, and then you can install it as an MCP server. You just pass it an arg of -c for the config file, and then path to that YAML file. And those tools will show up in your agent, and you'll be able to run those tools, and it'll execute the graphs. It's pretty slick. So I'm going to give you a quick demo of mcpGraph UX, which is a separate project. And this, to some extent, is a tool that you might actually use if you're developing this yourselves or if you're inspecting MCP graphs generated by agents. It's also just a good way to demonstrate all the functionality that we talk about in the underlying MCP graph around inspectability and observability. So I'll show you the graph runner. the visualization of the graph, some detailed tracing, and some debugging controls. So this is mcpGraph UX. It's a simple node application. I launched it with a path to my mcpGraph file, my YAML file. And so I can see over here the file utils, like I showed before. So that's the server this presents as. These are the tools it exports, just one tool called count files. And these are the MCP servers that it uses in its process. So when I click count files, it basically is going to make me a form that allows me to type my input parameters. And when I'm ready, I can run it. And I can see the nodes here, sort of what they look like. So let's just run this and I'll show you how this works. And you'll be able to see it animate through. It'll show you the active node. It'll stick for a second on list directories, and then it finishes very quickly. And then I can see over here what happens. So I have an entry count files entry node, an MCP node, a transform node, an exit node. And if I want to look at, say, the transform node, I can see that its input was the output of the directory node, which is this thing that came back from the MCP server. And I can actually see the context prior to that. So I can see the entry node, the directory parameter, and then the output was count 7, which is the final output, which is this count 7, which is what got returned from the MCP server. So that's unsurprising. Let's look at another thing that we can do. We can set a breakpoint and we can hit run. This time we'll run very quickly because once the MCP server has been loaded and the client is cached, you can see that took 3 milliseconds instead of a couple of seconds it took the first time. And now I'm stopped. I'm pending on this count files node. I'm stopped here in the debugger. I can single step this and go to the next node. Now I'm on this exit count files. I can resume to finish it. The other thing I can do is I can just single step through the whole thing if I want. So I can see I'm on entry count pending. I step through. Now I'm on the list directory node. Entry is finished. This is pending. I can see the input output. Sort of step through the whole thing one at a time. So nothing too exciting, but it's just giving the basic idea that we can visualize and inspect and sort of debug these things after we've created them so we can interact with them. And you can also build tooling. This is all done via API, obviously, so you can build tooling to do any of this kind of stuff too, to basically inspect and observe these graphs as they run. So I guess in conclusion, mcpGraph, I think, is a solution that has all the benefits of code mode, solves the same problem, and it does it without code. And I think the code, I think there are significant challenges with using code to do this. And I think being able to do it without using code definitely is going to be a lot simpler, at least for some use cases. So I think some things I'm still working on. I want to build out more. I've had agents generating these things, but I want to build out more skills and rules and prompts for LLMs, and also test those to just make sure that we can compose all these MCP graphs for all the example use cases, and that works more reliably. And then I'm going to build all the examples in the code mode papers and just demonstrate that those all work. So this is very early. It's only about a week in to this project, but it is fully functional, and I've been using it in some of my own workflows, and I'm super excited about it. So if this is interesting to you, give it a try. Let me know how you like it. Thanks.